Hello friends, good evening. Welcome back to Oil and Gas Data Analytics program by 360DigiTMG. So we are looking into data analytics which deals with oil and gas industry data. So we have started with applications. So we have seen what are the different applications of data analytics in oil and gas industry. Then we have looked into methodology. We call it as CRISP MLQ, okay, cross industry standard process flow, machine learning applications, which comes with quality assurance. Okay, so I have seen all six different phases that we have here, and we are we then looked into EDA part. Okay. So exploratory data analysis to find the patterns, hidden patterns in the data. Then we try to look into data pre-processing, which is common for any domain. EDA in data processing is common for any domain. It depends on the data, what data type I have, and if there are any missing values, if there are any outliers in the data. So I am going to look into all these different aspects, and based on that, I am going to prepare my data. So then we started the process of data mining. Then we started the data mining process. We are looking into unsupervised and supervised models. In case of unsupervised models, we have seen k-means clustering with a use case that is related to oil and gas data analytics. And when it comes to supervised learning, we started with KNN process. It's a classification model that we have used. Then we have looked into decision tree. Okay. So in these models, we have gone through all these different, for each of these model, we have taken a use case and we have tried to look into how this particular model works for this particular data, oil and gas related data. So today we are going to look into linear regression. So before that, we have to understand in case of supervised learning, when we are saying supervised learning, the first thing we need to consider that we will be having a x. Okay, we will be having a x variable. Okay, that is my input data. Okay, so I'll be having maybe there will be more values also. Okay, so I will be having x2, x3, right? So I may have the multivariate data also. Okay, so in the same way, in case of supervised data, I'll be having the output value. Okay. This is also called as target. Okay. It is also called as label. And basically, in this process, when we are working on linear regression, so here we call it as the input data is known as independent variable, and the output data is known as dependent variable. These two factors are very important. Okay, we have independent variable and dependent. Now we try to look into, is there any relation between my independent data, dependent data. Okay. So the commonly when we look into the data, y is equal to f of x is the common. Okay, this is the preliminary function that we are going to use when it comes to data science. Okay, when it comes to machine learning processes, okay, we are trying to compare. Okay, when we are trying to find the relation between x and y here. Okay, if I have something like profit, okay, if I have profit, okay, what I'm going to try to look here. So revenue minus expenses gives me profit. So if I increase revenue or if I increase expenses, this value will be changing. Okay. So in this case, my profit will be y and my input variable will be x1, x2. Right. So in this case, here again we have divided this data into two types here. Okay, we can take it as we have two types here based on my output variable. So when it comes to output variable, if I have data and if my output variable is categorical, okay, if my output variable is categorical, like yes or no, okay, finally I am saying that if my output is either yes or no, that is categorical. In this case, we will be using classification models. If we have this, we have already seen. Okay, we have used the classification models like KNN. Okay, we have done some lithology process. Okay, we have classified the data, and in the same way, these models okay, in if my data is numerical, if my data is numerical, okay, if I have some continuous data. In case of continuous data, the models, okay, we are going to use are regression models. Okay, we are going to use the regression models. We have like linear regression. Okay, in again, in case of linear regression, we have like simple linear, multiple linear, logistic linear. Okay, there are different methods. Okay, so there are different methods based on the data what we are looking at. In case of simple linear and multiple linear, here in case of simple linear, we will be having only one input data and output data. Input and output. That's it. Okay. And input values will be so we will be having a continuous data. Output will be continuous data. In case of multiple linear regression, I am going to have the output that is a continuous data. Along with the output, I will be having multiple input values. Okay. So this is the basic difference between the simple linear and multiple. Okay. So here we are going to use the regression. Okay, these are the regression numbers we are going to look at. So let us see what do we have. Okay, we have we'll be looking into regression analysis, linear model, correlation analysis. Okay, so what is the equation of straight line? Okay, simple linear regression, transformation process, okay, bias and various. And we'll be looking into what is multiple linear regression also, and we have business use. So when it comes to regression, what is we have to understand what is regression is. Okay, regression is used to study the relationship between two different variables. Okay, if I have two different variables, there will be some relation. If there is any relation that we have to study. Okay, so we can use simple regression if both the dependent variable and independent variable are numerical. Okay. And if the dependent variable is numerical, but the independent variable is categorical, again, we have some more methods, okay, based on the data. Okay, it's completely on based on the data, what type of data I am going to get. Usually the examples that I give when it comes to regression, like you can see here, uh, if we are testing, okay, if the testing, if IQ affects, okay, if IQ is the value. Okay, so IQ is the value. If IQ affects income, more IQ, more income. IQ is the independent variable and income is the dependent variable. Okay, generally we have like more IQ, more income. It is possible. Like testing if hours of work, okay, hours of work affects hours of sleep. Okay, so dependent variable is hours of sleep and hours of work. Okay, so maybe if you sleep less, maybe it may affect on your work. It may decrease, right? So this is also a possibility. And one more example is like testing if the number of cigarettes smokes. Okay, if you so if a person smoked many cigarettes, will there be any effect on blood pressure? Right. So so in this case, number of cigarettes smoked, okay, is one case, and blood pressure. Okay. So all these are some examples that are related to simple linear regression. Okay, I have one independent variable and I have one dependent. So this is something related to what is regression and how we are going to compare this data. So how do we take these values here? I am going to take these values in a scatter plot. Okay, here I have plotted IQ. Here I have plotted income. So what we have discussed is like if IQ value is increasing, my income will be increasing. That is general perspective, right? So what is happening here? I can see a straight line, okay? And all the values are lying. Okay. So this is nothing but a positive correlation. Positive correlation. This is called as a positive correlation. And as the income increasing and IQ increasing, we are having the line in this way. This is can be said as strong correlation. All the values I can see near this line. Okay. And it depends on the complete data. Okay, we may have data in this format also. Right. So these are different formats. Okay, in this example, we can see that the relationship between body fat. Okay, if we are taking that in percentage, and chance of heart failure is not linear. Okay, how we are going to get into this conclusion based on the data. So it's not a linear relationship. We are saying that it's not a linear relationship. But is there a relation between these two? Yes, there is a relation. Yes. But it is not a linear relation. So when it comes to when it comes to these analysis, okay, when it comes to scatter plots that we are taking and based on the data that we have, we can look into the data. So we can see that by these values, okay, by these values what we have, we can see here a strong positive correlation. Right? So I can see the data going this right. So in that way, we can see that my x value is increasing, my y value is increasing. Okay. So in the same way, here in this case, it is a positive correlation, but I can see some of my values are something like this. So there is some deviation in data, and if there is here in this case, if the scattered plot is in this way, we can say that there is no correlation between the values. As we have seen the positive correlation in this way, we may also have the negative. If this value is increasing and if my x value is decreasing, okay. So there may be chances. Okay, I can find this value. Okay, strong correlation, strong negative correlation here. Okay, and as we have seen earlier, so this is something called as curvilinear relationship. You can see a curve here. So we are trying to find the relationship between my x and y values. Okay. So scatter diagram. Okay, we use these scatter diagrams that provide. Okay, these plots provides a graphical representation of two continuous variables. If I have two different continuous variables, if I want to find the relationship between two continuous variables, I am going to use this. So here we have the linear model. Okay, usually the formula is when I say a linear model, I am going to take it as y is equal to mx plus c. Okay, this is the straight line equation. So if I have the data, I assume that I will be taking a best fit line, and the intercept that I have. Okay, when I have this, okay, the intercept that I have here is beta naught. Okay, this same value I can take it as beta naught plus beta x. Okay, so so the error value. Okay, we'll be taking the it comes with the error here. So we'll be having a y-intercept here. Okay, so it's the same data that we have taken here. Okay, we'll be having the y-intercept here. We'll be having the x is the independent variable that we have. Okay, y is the dependent variable we have, and a is an intercept. Okay, here the same formula is written in this way. Okay, a is an intercept. Okay, it is an intercept on y-axis. Okay, and b is the coefficient. Coefficient is something related to the slope value. Okay, how these values are changing. Okay, if my x value is increasing, is my y value is increasing. So there should be some correlation there. And E is an error. Okay, E is an error that we find out. Okay, E is an error term for each observation that we have. If I have some data. Okay, if I have this is my data. Okay, and this is my line. Okay, this is my if I am drawing a line here. So what is the difference between the original actual value and what is the difference between my predicted value? So these are the different values we have. So this is how we calculate. Okay, this is how we get the values. Okay, how we are going to get the error value? Generally, we know, right? So y minus y hat gives me the error. So we have seen the error function, right? We use this error function in case of the regression. So we are going to find the error. So when it comes to so we have when we are saying about the correlation here, no, we can calculate the correlation value. Okay, so we can calculate the correlation value, and if okay correlation values lies between, okay, we call it as correlation coefficient. This quantification that we are doing, okay, that is known as correlation coefficient, and the values lie between -1 to +1. So if I have +1, that is perfect positive correlation. And if I have negative correlation, that is nothing but it is a perfect negative correlation. And if I have this value as 0, we can see that it is a no linear correlation. So it's a non-linear correlation. Here we can see the example. Okay. So that we can see the positive correlation here, negative correlation here, and I have a formula based on which I can calculate my R. So based on the correlation, okay, based on the correlation, we are going to calculate the ordinary least squares regression. Okay, we call it as OLS. Okay, OLS is a common technique for estimating coefficients of the linear regression. Okay, if I have a linear regression equation to estimate the coefficients, we are going to use the OLS. Okay, which describes the relationship between one or more independent quantitative variables. It works with both multilinear as well as and a dependent variable. Okay, simple or multilinear regression, right? We are speaking. Okay, in both cases, we'll be taking into. So we can see here, okay, beta naught that we have. Okay, beta naught that we have, that is the y-intercept here. Okay, and when it comes to beta 1, okay, beta 1 is nothing but my slope value here. And x naught, okay, x naught is the value you can see here, a specific value of x, the independent variable. Okay, we have the independent variable here, that is x naught. Okay, and the straight line equation that we know is y is equal to beta naught plus beta 1x. And the fitting a straight line by least squares. What happens here? We are going to take the difference here. Okay, based on the different error, this is my predicted value. So the equation for the predicted value will be y hat is equal to beta hat, okay, beta naught hat plus beta x hat. Okay, so these are the values again. So what we are trying to do here, these values, okay, these values what we are seeing here are an observed value of x. That means, so these are the original actual values. Okay, original actual values when x is equal to x naught. Okay, so when x is equal to x naught, these are the original values. Okay, the mean value of y when x equals to x naught. Okay, so this will be my mean value here. Okay, based on that mean value, okay, we will be calculating the error term. So the difference between this value and this value will be my error. So in case of simple linear regression, okay, so we will be calculating the R squared, okay, R squared, which is also known as coefficient of determination, okay. So in this case, it represents the percent variation in output, okay, when it comes to the dependent variable, how much percentage it is varying, okay, and it is explained by input variables or percentage of response variables. Okay, what is the variation that we are going to see here, and variation that is explained by its relationship between one or more predictor variables. Okay, so here the R square. Okay, here the R square. It is the R square gives me the better model. Okay, if I have if I have the higher R square, if my R square rate is high, I can say that the model is better. Okay, the better the model fits your data. Higher the R square value, the better the model fits your data. So when it comes to R square, it will be between 0 and 100. Okay. And if R square is between 0.65 to 0.8, we call it as it has a moderate correlation. Okay, we call it as a moderate correlation. And if R squared is greater than 0.8, we call it a strong correlation. Okay, so we have a formula where we can calculate R square here. Okay, we'll be calculating, and we can see here R square value. Okay, it is like it is less than. Okay, it is less than or equal to 0. It is less than or equal to 1. Okay, it will be between these values as we are seeing both 0 and 100%. So when it comes to the when it comes to the taking the continuous data into consideration, okay, when we try to find the probability, okay, probability distribution, we will be seeing that these values, okay, these values will be from minus infinity to plus infinity. Okay. So we'll be considering these based on the standardization. Okay. So standardization will be taking these values, and based on that we'll be calculating the Z table. Based on the Z table, we'll be calculating the values, and we will be getting the confidence interval. Based on the confidence interval, we take these values in such a way that the values that we are taking that will be falling in this particular confidence. Okay, so these factors will be considered. Okay, so prediction and confidence interval are types of confidence intervals used for predictions in regression and linear models. And when it comes to prediction interval, it represents a range. Okay, it represents a range that a single new observation is likely to fall given specified settings. So, what is the range here? This will be the range, and this range will be getting based on my confidence interval. And when it comes to confidence interval of the prediction, it represents a range that means that mean response is likely to fall given specified settings of the predictors. And the prediction interval is always wider than the corresponding confidence interval. Okay. So these factors will be taken care of. And as we have discussed earlier, when it comes to simple linear regression, my output variable will be continuous. Okay, I'll be having a continuous data here. Okay, when I have a continuous data, my x, okay, x is nothing but the input data, independent variable. Okay, I'll be having a single independent variable, and it will be continuous data. Okay, this is nothing but linear. Okay, simple linear regression. And in case of if I have the continuous data as my output data, and if I have values simple and discrete, what I have to do? I have to convert this data into numerics. Okay? I have to do the conversion. So when it comes to multilinear regression, okay, it doesn't change. Okay, the equation that we take, that remains basically, but we will be having multiple values here. We'll be looking into multiple values, multiple independent variables here. Okay, input values. Based on that, we are going to calculate. So we need to consider four things here: linear, independent, normal, and equal variance. These are the few factors, few parameters that we need to consider. When it comes to linear, we assume the assumptions about the form of model. Okay, we assume that the model is linear. Okay, all different linear parameters that we have that will be taken into consideration here also, like residual sources, fitted values, observed values versus predicted values. All these values will be taken into consideration. And when it comes to assumptions, okay, what are the different assumptions we are going to take? We will be looking into IID normal, okay, independently and identically distributed. That means when it comes to the values, okay, so we'll be taking them as independently and identically distributed values, okay, and we'll be considering zero mean, constant variance, and if no constant variance is there, if there is a constant variance is there, so we call it as homoscedasticity, and if there is no constant variance is there, we call it as heteroscedasticity. But these are all factors that should be taken into consideration and independent of each other. Okay, these values should be independent of each other. If not independent, it is called as autocorrelation problem. And there are several assumptions about predictors also. Right. So when I'm saying predictor, about the output data. Okay, that should be non-random value. Okay, and measured without error. It should be measured without error. And linear independent of each other. If not, it is called as collinearity problem. Okay, we will be removing. Okay, if there is a collinearity problem, we will be removing that particular column and we'll be working. So these are few model assumptions when it comes to the multilinear regression. So how the data will be, we can see here, the data will be in this format. Okay, we have y continuous. Okay, y, what is y here? Y is the output data, and my input data will be multiple values, and I'll be having a continuous data. Okay. If I do not have the continuous data, what I'm going to do? I am going to convert them to my conversions. Okay, this is nothing but the multilinear regression we have. So, how do we find the error? Right, the error is also very important. Okay. Error variable, like, okay, with the required conditions. What we are going to look into here. So, the error is a critical part of regression model. Okay, we are going to get the error. Okay, four requirements involving the distribution of E. Okay, that is error. Okay. The probability distribution of error is normal. That should be normal. The mean is okay. The mean of error okay, the mean of error is 0. Okay, and the standard deviation of error is for all values will be x, and the set of errors associated with different values of y are all independent of each other. So these are few things that we consider when it comes to error variable. To explain this, I have taken a use case that is related to share market. Okay, so it is something related to US oil and gas share market, where I have used the linear regression algorithm. So the different attributes that I have here are date, symbol, open, low, close, volume, and currency. So here it speaks about the date. Okay, date is nothing but how these values are. So this is the sequence value. Okay, it's a sequence value, but here we call it as a panel data. Okay, so it is also called as longitudinal data here, and we have symbol. Okay, these are the different companies I have. Okay, I have taken different company data based on the date, what is happening. Okay, what is the opening share price and what is the closing share price, and in a day, how much peak it went. Okay, if the open share price I'm seeing here, it is 39.75 for a company, and it has reached maximum up to 40.38. Okay. So here we are looking into intraday sale. Okay, every day 2103. The company's name is Exolo. the opening sale price was 39.75 and the closing sale was 39.16. Okay, so it has closed some loss. Okay, we can see that it has closed some loss, so it has decreased, right? So the closing was acceptable. Okay, we will be looking into closing and opening factors. And in this row, we can see here, if I want to explain this particular data, okay, we can see here that the opening price was 39 and the closing price was 40.50. So it has closed at very good rate. Okay. And we have the volume and the currency. Okay, it's a US related data that we have taken here to explain this. And we have taken some common Python libraries like pandas, numpy, matplotlib, and other things. And for we have taken a scalar for the linear regression modules, okay, model what we are working on. So when it comes to EDA, we have looked for any what are the unique values we have here, okay, and we have looked for data types, okay. We can see that date is the object data, remaining all we have in a float format. And are there any NA values that also we have looked at. And we can see how here we have tried to see the distribution of data, what is happening, okay, throughout a few data we have taken, open and the density, okay, the number of stages we have taken, and based on that we are trying to find the what is happening here. You can see the data is increasing and there are a lot of fluctuations in data. When it comes to volume, the whole, okay, how the data, how the complete data is distributed. Okay, in my whole data, what I have taken, data set what I have taken. So these, the open, high and low and close, all this data, if I see here, it's okay. Okay, not much. I can see that some data is leaned. Okay, most of the data I can say, most of the data is leaned towards left side. But in case of volume, you can see there is a peak in the data. Okay, there is a peak and is completely leading towards my left side. Okay, so these are right skew. Okay, most of these are right skew. Maybe here the value will be more, but the value will be less when it comes to these data. So here in this case, we are trying to look into the outliers. If there are any outliers, as we have seen that there is a skewness in my data. Yes, obviously I have outliers in my data. And here we can see that what is the trend? Okay, what is the trend that is going on when we have taken the open? Okay, open is the only column I have taken here, and I want to see the trend. Okay, and these are different companies I have. So we can see that 2000 it has opened somewhere around 10K. Okay, and as the values increase somewhere around like 2017 or 18, I can see that it has almost reached to 40K. Okay, so these are a few, this is some analysis that we are trying to do by taking the time into consideration and how the open value are changing. And just here we have tried to look into the data that is related to oil and gas, the stock attributes. Okay, different values I have taken here, open, high. So how these values are changing. Okay, what is the fluctuation? You can see a huge fluctuation in the data. It's a timeline. Okay, we have taken some timeline from like 20 years. So there will be many things might be happening. So we have the data pre-processing. Okay, in case of data pre-processing, we have tried to convert. Okay, we have used a label encoding, and here I have something like currency. Okay, this particular column I have converted the data. And data splitting. Okay, so when I'm working on my supervised model, okay, so I have to do my data split here. Okay, so for that first I have to represent my output value and input value. Here I can see that my input value, okay, so my here I am taking my output value as close. Okay, I want to determine the close value. I want to predict my close value. So remaining all values except my close value will be my independent variable. So we are working on multilinear regression, and I have taken the test size. Okay, the test size we have taken it here. Okay, that is 0.25. Okay, 0.25 is the split. Okay, 75-25 is the split that we have. And model building and evaluation. So here we, as you can see here, we can use different regression models. Okay, we are trying to use all these different models here. Okay, for example, we have decision regression or random forest regression. All this we can use, but in our case here, we are working on. So here we are looking into linear regression. So I am trying to import linear regression here. Based on that, I am going to. So here I am feeding my model. Okay, my model with my data, my input data, output data, and here I can see that what is my R square score. Okay, here I can see that it's like 99.9. Okay, so we have seen if the value is near to so we take these values from 0 to 100%, right? So here I can see that this is 90.9. Okay, I think it's a best fit model that we have created. So let us look into same details in the program. Okay, what we have worked out in the program. So I will be showing this program in Google Colab. So here we have the program. So initially we started with importing the different margins that we have. So here we have imported different modules, pandas, numpy, mapper, cbot, etc. Right? So and here we have taken the data. Okay, this is my data. I have taken my data here. In my data, I can clearly see that these are different attributes I have. Okay, date, symbol, open, height, low, close. Okay, these are the different values I have. And so this is the data I am looking into. Okay, this is a sample data. If I want to look into one sample data, I can do that. Okay, now I am taking my uh, initially the data. Okay, so df is my data set I have here. Okay, if I want to look into unique values, yes, these are my unique values here. Okay, and value count. Okay, if I want to count, okay, what about the value counts here that I am going to look into. And what are the different data types I have in my data. Okay, how many float data types I have. If I want to look into that also I can do that. So this is all part of my ED. Okay, I'm just looking, I'm just understanding my data, what I have here. So these are different data types I have. Okay. And so we have taken different values here. Okay, DF, what are the unique values? Are there, do we have the unique values or we have duplicates? Okay, so that we are trying to look into each and every column here. Okay, so if based on if there are any NaN values that we have tried to replace that values. Okay, and here the currency. Okay, currency is like it is USD. Okay, so we have tried to create all these values should be USD. Okay, if there are any changes, it will be converted to USD. And if there are any outliers in my data, okay, if there are any outliers in my data, I want to look into that aspect also. So finally, after doing all these analysis, okay, so we can look into the data here. Okay. And if there are any missing values in my data, okay, so all this, okay, if there are any that aspect also, we have to look into data. So each and every value, what is Qness, what is the Q1 value, Q2 value, each and every row, we have taken the data. Okay. For example, if I am taking row is the column, I can say this is the Q1 value, Q2 value, Q3, IQR, okay, and all this data. Okay, mean value, median value, mode values, Qness, curtosis, all this is part of my ED. Okay, statistical analysis that I am doing here. Okay. So yeah, we have seen this. I want to look into the distribution of data, how my data is distributed. Then when I have taken the box plot, I have seen that there are certain outliers are present in my data. So I have used a AutoVis. Okay, it is a auto EDA process, auto EDA function that I have here. I have imported that package and I have tried to look into my data. Okay, and I have applied. Right. So we have got a colorful graph here, which shows me about the stats that are related to my open column, the total trading open distribution of major US oil companies. Right? So how it is open? We can see here each and every value we can notice here. Just look, what is this? So it is SLB is the company and the date is April 28 and between June 2018. So the open, okay, sum of open value is something like this. So we have added all the data based on the by adding all the data we are looking to. So 1 month each month data. This is okay. Each month what is happening here. In the same way, the high values. So, okay, up to which range the data went. That also we have added and we have got these values. And we have looked into the oil and gas attributes. What is happening here? All these factors. So the fluctuations. Okay, from beginning to end, what is happening? That fluctuations we have tried to look into. And the volume trend. Okay, what is happening? Okay, I have taken only the volume color and I am trying to look into the volume trend here. And we can see here the distribution of open prices with in context with US and gas stocks. So we can see the distribution what is happening here. Only I have taken the open prices here. Opening of share, right? Opening market share. So what is the price and how it is distributed? That we are trying to. And when it comes to close, okay, with the different companies, okay, when it comes to different companies, what is the closing value? Is it high or low? Okay, so we can see there are few companies that have always been closing very low, but there are few companies that we are seeing here. Okay, it may be same companies also when we can see the red color. Okay, okay, so maybe sometimes it is low and high. That is also possible. And the stock price from 2000 to 2022, we can see here. Okay, it's a 3D representation, and we are trying to look into some correlation scatter plot here. Okay, in 3D format. Whatever the companies, okay, we can see that this red color that is the cluster we can see here. It is about the CVX. Okay, the date is March 22, and volume is something. And when it comes to lowest value, it is 3.47. Okay, this is the closing data. The closing is 120 and here closing is 5. Maybe if you look here, the closing is 76. So we can take the heat map here. Okay, we can take the heat map and we can try to look into the correlation factors between all these different factors. Okay. Here we can see the bar. Okay, one. Okay, when it is blue. Okay, what values I have? So these are correlated data. Okay, I have got the values here. Most of these are correlated. The high and low, all these values are very correlated to each other. So now, all based on this, what we can see, these values are very important. Okay, correlation. You can see that all these independent variables, we have correlation. So all these values are important. Okay, the numerical data that we have. So in the same way, if you want to find the correlation, we can see it clearly. Okay, the same plot we have taken again, so we can see the correlation is one here, and these also. Okay, these are very least correlation vector. When it comes to volume and the other factors, the correlation is low. But when it comes to volume and other factor, okay, open, okay, except volume, there is a high correlation. Yeah. So we have taken seaborne to represent a few okay pair plots here. You can see we have taken the scatter plot as well as okay, we can see here uh, clear correlation we can see between open and close, right? These straight lines that we see here and how the data is distributed. That also we can notice. When it comes to volume and other factors, uh, there is no much correlation that we can notice here, right? So all these same thing we have seen in our values also. And whatever values I have, okay, symbol and currency, I am trying to convert that into label encoding. So I have given the labels. I have 7 different companies. I have given 7 different labels. And yeah, building the model. So I have split the data. I have taken the percentage as 25 and 75 when it comes to train and test. And I have imported all my required uh, uh, values here. Okay, all my required. Okay, I am performing the regression. Okay, linear regression here. Okay, I have imported linear regression module and I have given my data. So based on my data, I can see that. So the R square value that I have got here is 99.9%. Okay, this is the best fit. Okay, we can say that this is the best fit. Okay. Higher the R square value is, the better the model is. So clearly we can see that the R square value is higher. So this model, okay, with for this data, this particular model that we are using here, that is the best fit here. So today we have looked into linear regression. Okay, so in case of linear regression, okay, we have today we have looked into linear regression problem. Okay. So in case of linear regression, we have seen the simple linear and multiple linear. In case of simple linear, we will be having one independent variable and one dependent variable. In case of multiple linear, we'll be having multiple independent variables and one output. Okay. So that is the major difference that we have. Okay, we take based on the straight line equation, we will be fitting the best fit line, and based on that, we are going to get the data. And we will be calculating. Okay, we'll be taking the error function into consideration, and based on the error value, we'll be taking the best fit. The least error value if I get, that is the best fit. So tomorrow we are going to look into neural networks. Okay, neural networks, something. So we'll be looking into ANN. Okay, artificial neural network, and we will be taking one of the use case, and we will be trying to explain using this use case, which belongs to oil and gas industry. Okay. Thank you, friends. Thank you for your time. Let us meet tomorrow for the next session that is belonging to oil and gas data analytics. Thank you.